Hello everybody, and welcome again to some hints on selected problems for your semester 2 review. Let's get started. The first few problems deal with the idea of work. Recall, work is done by forces. If the force and the distance traveled are aligned, then we have positive work, as in the case of a bellhop lifting up a suitcase upward because the force is up and the distance is up. If the force and the distance is anti-aligned, then the force is up and the distance is down, and theta, the angle between the force and the distance, is 180 degrees in this case. Cosine of 180 is -1. So here we are looking at a force times a distance times cosine of 180 minus 1. Negative work here, positive work here because the angle is 0 degrees. And at this spot, the angle between the force and the distance as the bellhop carries the suitcase along is a 90-degree angle. Cos of 90 is 0, so here we have 0 work done. Remember, work is measured in joules, so 0 joules during this phase, some positive amount of joules here, and some negative amount of joules here. We can also look at the work done by the gravity force, and the gravity force, of course, is straight down at all 3 locations. And the analysis is the same. Look at the direction of the gravity force, look at the distance traveled, evaluate the cosine of the angle in between those, and that will tell you whether you're doing positive work, negative work, or 0 work. Remember that the reason that we study work at all is to learn about changes in energy. We developed 3 different equations for energy, one for kinetic energy, the energy of motion, one for the stored energy, the energy stored in a gravitational field, and we also, although it's not useful at this stage on this problem, but will be later on, the potential energy stored in a spring, 1/2 times the spring constant times the stretch distance squared. Here we're looking on question 5 as to what happens to the energy as it falls. Well, the kinetic energy is going to be increasing because the velocity is increasing, and the potential energy is going to be decreasing because the height, as measured from the reference point of the ground, is decreasing. But the one thing you can count on is the potential energy plus the kinetic energy will stay constant. Imagine 2 bars on a bar graph, and one might represent kinetic, one might represent potential, one might be on its way down, the other might be on its way up, or vice versa. But the point is that the total amount of energy in a closed, isolated system remains constant, does not change. On question 7, we follow a ball that is thrown vertically with an initial speed of v0, and we're trying to figure out this graph, the second graph down here, the kinetic energy, as a function of time. To help us understand kinetic energy as a function of time, recall that kinetic energy is 1/2 mv squared, and it's easier to think about what's happening to v as a function of time. So at the beginning, at time equals 0, we do have some speed. It's not 0, it's moving. And what happens to the speed as time goes by? It increases faster and faster and faster. Notice we're talking about speed here, which is the absolute value of the velocity. And the reason why we don't worry about the sign of this velocity, whether it's positive or negative, is because in a moment we're going to be squaring it, and so even if it is negative, the kinetic energy will still come out as positive. So indeed the velocity does, or the speed I should say, does increase as time goes by, and it does so at a nice steady rate. And in fact, you know that rate. It goes 9.8 meters per second faster for every second. 9.8 meters per second per second. So now let's see if we can apply, now that we know about the velocity, what happens to the kinetic energy. Well, you might recognize the form of this equation as looking a little bit like y equals ax squared, which you should recognize as being a parabola shape. The same thing's going to be true for the kinetic energy. But recall that it's not true to say that there's no kinetic energy at the beginning. There is some, because there is some velocity at the beginning. I'll let you take it over from there. Next question. Question 8 asks you to identify the differences between a transverse and a longitudinal wave. Recall that a transverse wave is the kind that's most people think of when they think of waves. It's the kind that goes up and down. Notice that the vibration is up and down, but the direction of travel is sideways. What kind of things are transverse waves? Like water waves, light waves, and a bunch of others. Longitudinal waves, on the other hand, the vibration is back and forth, left and right, and the direction of travel is left and right. Longitudinal waves have areas of compression where everything's all kind of bunched together, and then areas where things are expanded and then compressed again and then expanded. And we see this in the case of sound waves. The gap between a compressed region and the next compressed region is the wavelength. We also saw this when we had the slinky vibrating on the ground, and we saw that the slinky was stretched and then compressed and then stretched and then compressed. That too was a longitudinal wave. Next question. First of all, pardon my pathetic pendulum, but the idea is okay. Let's take a look at the energy as a pendulum swings back and forth. At the bottom, the pendulum is moving at maximum speed, but has no height above its lowest spot. So at that spot, it's got pure kinetic energy, pure 1/2 mv squared. At the top of the arc, it's got pure potential energy, pure mgh, no velocity. But at this point right here, at this midpoint, it has a mix, some potential and some kinetic. The kinetic here is a bit less than this kinetic. The potential here is a bit less than this potential. But one thing is for sure, is that if energy is being conserved, if it's not becoming bigger or smaller, then this kinetic energy must equal both of those, or this potential energy must equal both of those. In other words, the energy never changes. In this problem, you're being asked to solve for this kinetic energy. But since you can easily calculate this potential energy and this potential energy, and you know that they're equal to each other, you can use this equation, equal sign, sideways equal sign, to solve for the kinetic energy at this location. On problem 13, we look at another conservation of energy type problem. Here we're being asked to find the kinetic energy just before it hits the ground. But we can take advantage of the conservation of energy, and we can find how much energy we have here and recognize that it must be equal to the amount of energy we have here. At the top of the flight, we have two kinds of energy. We have some kinetic energy, because it's got some velocity, and we have some potential energy of gravity. And we can choose as our height, we can say this is our reference height of 0 here, so it's got 20 meters of height. This is the kinetic energy at the top, and this is the gravitational potential energy at the top. And we know that the energy there must equal the energy at the bottom, but at the bottom it's purely kinetic. So we can solve for the kinetic energy. That's what the problem's asking to do. Next question. This is a quickie, question 15. The speed of a wave depends on one and only one thing. We've talked about it at length. Nothing else matters. One and only one thing. Should be in your notes. Good luck. Next question. Question 20 asks about what the Doppler effect predicts for approaching sources and for receding sources. Remember, Doppler effect tells us about perceived frequencies. Your clue for question 20 is this. Here comes a race car. And there it goes. What can you say about the frequency? Next question I'd like to discuss is the one about plane mirror images. Here's an object. We know where the image would be. It would be equidistant and behind the mirror. So here's the image. Same size. And then we ask some questions. Is it upright? Yep. And if it's upright, it's always virtual. And that should get you through that question, which was number 22. Remember, in all cases, uprights go with virtuals and inverteds go with reals. Okay, for question 27, we've got a horizontal force F that's pulling this block along. It's a 10 kilogram block. And it's pulling it at a constant speed. When you see the words or the phrase constant speed, the first thing that should pop into your mind is what about the acceleration? Zero acceleration, not accelerating, going at a constant speed, which means the net force, which equals ma, must also be zero. So that means the up and down forces must be balanced, and the right and left forces must be balanced. If this force is bigger than 30, you're accelerating. If it's less than 30, you're slowing down. We want one that produces constant speed. So that means our F is 30. Notice that our force and our distance are aligned, so we know how to handle cosine of theta. And the last thing to worry about is the distance traveled when you go at 4 meters per second for 1 minute. So you have all three of those things. You're ready to figure out the work in joules. Question 38 asks us to think about the energy in a block spring system as it's going back and forth. So it's oscillating between the maximum stretch position and the maximum compression position. And we're looking for, first of all, where the potential energy is equal to a maximum value. And that will equal a maximum value when the x is at its largest value. X is 0 when it's at rest, unstretched. When x is this way, we're positive. We have big positive x's. So we have a big potential energy to spring, ready to snap back the other way. And when it gets compressed, x is big and negative, but it gets squared. So we have a lot of stored energy there too. But as it races through the middle, for a moment, there's no stretch at all, no stored energy at all in the spring. But there is an awful lot of velocity. The tricky question is to think about is where does the balance shift? Because at this side here we've got lots of potential energy, and here we've got lots and almost no kinetic. Here we've got lots of kinetic, but almost no potential. Somewhere in between here there must be a spot where the potential energy and the kinetic energy are equal as it loses potential and gains kinetic. To help you think about that spot, remember that the potential energy depends not on x, but x squared. If it only depended on x, then it would be midway in between would be the location that you would find potential and kinetic being the same. But it depends on x squared. So I'll let you ponder that one. Remember, in the potential energy formula also, a little sidebar, the K represents how strong the spring is. If you apply a force to the spring and you measure how far it stretches, and you do that for a bunch of different forces and a bunch of different stretches, you end up getting a straight line, and the slope of that straight line is K, the spring constant. Big values for big heavy springs, small values for little springs. Let's skip ahead to problem 41. This problem asks you, what kinds of things affect the perceived frequency? Well, it's these kinds of things affect the perceived frequency. Things like the original frequency, the velocity of the observer, and so on. If it's on the right side of the equation, it evidently will have an effect on the frequency which is perceived by the observer. Let's move on to question 43. This question asks, what happens to a beam of light as it transitions from air into water? And I would advise you to look on our whiteboard under the topics labeled wave behavior. One of those addresses what changes as we look at its velocity, its frequency, its wavelength. Some of those things change, some do not. If you have forgotten, take a look at the whiteboard and you'll see a clue about wave behavior as you change from one medium to another. Question 47, skipping ahead, asks about the distance traveled. If we know the amount of work that's done, 200 joules, by some unknown force working against gravity. Well, if you're going to be working against gravity, that force has to be just as big as gravity, maybe a itty bit bigger, but basically 70 newtons going up against gravity. And so we know the work done, we know the force involved, if we assume that 70 newtons is the correct value. And the cosine of the angle in between this force and this distance, you can see those are aligned. So you should know the cosine of the angle. So in our work equals FD cos theta equation, the only thing we don't know is the distance. Moving right along. In the last question that we will discuss here, question 49, you are asked to find the kinetic and potential energy of a diver at a height of 2 meters above the water. This again is a conservation of energy type problem. Take a look up here. You should see only one kind of energy, potential energy of gravity. As the diver plummets to the water, that potential energy of gravity will become less. The kinetic energy will increase from 0, but whatever this value is here should equal these two guys combined if the total energy stays the same. So we're comparing two locations, the top and the 2 meter mark, and the total energy should be equal. At the top we only have UG, and at the bottom we have UG plus K. Remember, this is UG at 7, and this is UG at 2. And we're being asked to solve for the K. The UG, the potential energy of gravity at 2, we can solve directly because we know the M, the G, and the H. Alright folks, that concludes the hints from the paper review I gave you. There are other questions on the test that were not mentioned on the review, the ones that said things like no question for this item, and we shall discuss those a little bit in class. Since you were extra studious and spent the time looking at this video, to reward you for your efforts, you can show me that you watched it and I will give you a little extra bonus on top of your bonus if on page 1 of your review you draw the top a sun, and on the very back page of your review you draw at the very top a moon. Crescent moon, please. And if you do both of those, I will presume that you watched quite a bit of this video and you will get a little extra credit. Bonus on top of bonus. Good luck everybody on the final. I hope you do great. We're on the same team. You know I'm rooting for you. Good luck.